Hi everyone. So here we'll be solving another problem on binary search, which is aggressive cows, and this is one of the highest rate, like highly rated problem, and like highly demanded problem when you're trying to like Excel binary search. So you can find this on SPOJ. So let's see this what it says. So here this is your test case, let's say, and 5 and 3. So you are given some bands. What do you mean by bands? Let's consider them that. So like not bunds, so one bund it will be having n stalls. So here you are having 5 stalls, which means these, let's say, these are rooms where you can keep cows. So we are given 5 rooms where you can keep this number of cows, c number of cows. So you are given 5 rooms, consider them as rooms. So these 5 rooms, you have to keep 3 cows in these. Okay, and you are given also the position of these rooms. Okay, like on a number line, if you consider them on like x-axis, they are given the position that at 1 2 8 4 9. So and on these, so 1 2 8 4 9, on these positions these houses are located. Now what this question asks is, these cows are pretty aggressive, so they want to be placed as farther as possible. Okay, so what this question asks is, this question asks us to give us that distance if so if you keep all the cows, let's say the possibility, if you keep all the cows here, so the minimum distance between any two cows in any possibility, let's say here if you see the minimum distance in this possibility is between these two cows, which is 1. Again, the minimum distance is 1. Minimum distance is 1. Minimum distance is 3. Minimum distance is, again here you see 3. Minimum distance is 1. So what this question wants us, amongst all the possibility, the maximum minimum distance, the largest minimum distance, you see the largest minimum distance is 3. Okay, so we have to we have to maximize the minimum distance. This time maximize the minimum distance. If you remember my allocation pages, there we have to minimize the maximum pages. Here we have to maximize the minimum. So what I'm saying, guys, in brute force, like obviously you can go with recursive and other solutions, but as I say, go with that brute force that you can optimize, that you can do some optimization upon. Okay, now see what you can think of here. So what you can think of here, because you want the minimum distance that is actually the greatest among all these possibilities. So what I say, can you think in a way that let me try to keep cows, because what I'll do in brute force, wait, let me just use this 1 2 8 4 9. 1 2 8 4 9. Okay, and we're having c cows and k houses, k stalls. What I'm saying, let me put all these because look, you cannot put all the cows in zero distance. Like you cannot make zero distance between them, because zero distance means all the cows are in same stall, and it is not correct. So let me try to put all the cows in like let me try to put all the cows in a way that the minimum distance between them is at least 1. Can I put them? Let's see. I call a function, I make a function canFit, and it will take all this observation, all these arguments, cows. It will take this array, and it will take your current minimum distance. Okay, so what you want, let's say minimum distance that you need right now, and your array will be given, like positions, and your number of cows will be given. Okay, so what I say, because you want this, you want the you want to maximize the minimum distance. So we will go with this, let's say 1. So can you put all the cows in such a way that the minimum distance, like the distance between them is at least 1. So here if you try to put because you are having 3 cows, so let's see this number line. So the first house is at position 1, second is at 2. Which is third house is at position 4, because 4 is the position. Okay, obviously fourth house is at position 8, then 9. So what I say, can you put all the cows in such a way that the distance between them is at least 1, so which means the minimum distance here between them would be surely greater than equal to 1. Okay, so for 1 we are checking. So if you see, you place 1 cow here, second cow here, so obviously the distance is 1. Between them the distance is 1. We want at least 1, so obviously we are getting the distance between them is what, 2. So you can put 3 cows here, 1 2 3. So yeah, you said that I can put. Now go for 2, check for 2, because this is a brute force, guys. We'll do whatever lengthier solution we can do, but we'll just find our answer for 2 distance. If I try to put the two distance between them. Can I put all the cows in such a way that the distance between them is 2, at least 2, between any two pair of cows? So let me put this cow, because obviously you will put this cow here. First cow will be at first position, because you want to put try to put these cows as close, but keeping the point that this distance should be at least greater than this minimum distance whatever you are giving in canFit function. So this canFit function will return either true or false. So for 1 it return true. Let's see for 2. You put first cow here, second cow you cannot put here, because 2 minus 1, the distance is 1, but you have to keep the distance greater than equals to 2. So you will go to this position, the next house, which is 4. Remember guys, this is why I initially shorted this space, because we have to go one after another. We have to see where we can put easily. So if you put 1 here, then you put 8 here, it is not that feasible. So that is why we try to short this array initially, because on a number line, if you see, these are the correct positions of houses. Okay, so if you put first here, first cow here, now where second cow would be, obviously it cannot be at this 2 position. Now see, 4 minus 1, it is 3, and what distance you wanted? For 2 distance you wanted. So obviously you can put your second cow here. You can put your second cow here. So second cow you'll put here. What for third cow? You can put third cow here. 8 minus 4. 8 minus 4 is greater than 3. The distance is greater than equal to 2. Third cow you can put here. Now see, minimum distances where you need to calculate between which pairs who are adjacent. Obviously 1 and 8. If you are able to put 1 and 4 cows on 1 and 4, so you don't have to consider cows between 8 and 1, because this will obviously be greater position. Their distance will obviously be greater than 8 and 4. So you have to consider only adjacent cows while calculating this minimum distance, that can they fit or not. So again, this canFit function will return 1 for 2. Now let's go for 3. Can I put cows in such a way that distance between any two pair is at least 3? If not more than 3, then at least 3. Okay, see, first cow you can put obviously here. Second cow, 2 minus 1, no. 4 minus 1, obviously you can put second cow again here. Third cow, 8 minus 4, you can put. You also got 1 for this. You are done that, yeah. I can also fit here. For 3 we are done. Now let's see for 4, because we have to maximize this minimum distance, correct guys? That is why we are increasing this minimum distance, but one by one. Okay, now say this 4. For this 4, let's see, can you fit all the cows? You are giving this in canFit function. Can you fit all the cows in such a way that the minimum distance between them, the distance between any two cows is greater than at least is greater than equals to 4, or if not greater than at least 4. So the distance between two cows should be at least 4. Can you find this? If you are able to find, then you also know that 4 is also my minimum distance right now. So you'll go to 5 as we did for 1 2 3. Now see, if you put, let me change my pen. If you put first cow here, so because you need 4 distance, so you cannot put here 2 minus 1, 4 minus 1 is 3. No, you cannot put 8 minus 1, 7 is greater than equals to 4. So you can put second cow here. But what about third cow? 9 minus 8, no, it is not feasible position. So you are not having any of the stalls left. So you can say that you are not able to place third cow here. So this canFit function will return what? False for this 4th. So if you are trying to put these cows in such a way that between any two cows there should be at least 4 distance. So right now your minimum distance, if you see this, your minimum distance can never be 4. And see, for 4 you didn't got. So will you go for 5 and 6, or like say 5 6 7 8? Can you go for what I said? Think in a way that if your minimum distance between 1 and 2, you try to keep 4 between these two cows. Let's say these were the houses, this were the space, and third cow was not able to fit in here. Third cow was not able to fit in this array space, sorry, on this number line, which was X obviously, and your stalls were located amongst these. So if now what you will do moving forward, what you'll do, you will try to increase the distance between any two cows. Okay, for in every two cows, between every two cows, you will try to increase the distance. So if you again try to increase the distance between these two cows, so you'll push them, because you have to, because look, this cows, let's say keep this as stable, because it will be obviously be 1 at position 1. So this cow will go some other index to right. So obviously if your second cow, if a third cow was not able to be in this third space, in this space, now the second cow will itself go to some more right. So how can this third cow come in here? This third cow will never be able to be in this space again. So once you encounter a index, sorry, once you encounter a value which with which you are not able to fit cows with at least this distance between them, if you keep this 4 distance, so if you increase the distance from 4 to 5, 6, 7, 8, so obviously all the cows, because with 4, which was the lesser distance, if you're trying to keep all the cows in this lesser distance, you're not able to keep them in one place. So if you increase the distance between them, see guys, just see this in analogy, if you increase the distance between them, so this second cow will itself will be having a hard time to fit in this array. So how can you say that third cow you can even think of? So from 4 onwards, none of these distances, if you try to keep the cows in this large distances, because this was obviously a smaller one, so this large distance, third cow, this large distance, if you try to put all the cows together, they'll never be in that space, okay, with at least 4, 5, 6, 7, 8. So what I said here, see guys, all these regions all these regions are your favorable regions, okay, all these regions are your favorable regions where you can at least put your cows in those stalls. And if you increase the distances between these two cows, and this canFit function will give you that information. For 4, you know this was unfavorable, you cannot put. So after this 4 onwards, all these functions, all these values will return what? 0, that you cannot fit all the cows at these stalls, so all these will return unfavorable. Getting it, guys? And see this, think of this, that why after 4, if you put, because you are increasing the space between them. If you see, let's take a case where that you are trying to fit something, some 2 balls on this number line, and if you increase the space between them, which means the distance you're increasing, so obviously this number line, this number line is static, this number line is fixed, so these balls will try to go somewhere else. So now what happens, these balls will be having hard time to fit into these, so they'll cross the boundaries, so that, and they'll not be inside this space. So that is what, if you increase the search space, sorry, if you increase the minimum distance between two cows, if you increase the minimum distance, so because with 4, if you're not able to put, if you increase the distance, so with all the increased distance, you'll not be able to fit all these cows, what I'm saying is all these cows you'll not able to fit in the space, limited space, because you are increasing the space between them, you're increasing the space between the cows. So now see guys, if you try to, like what we did on the number line from 1 to n, what is the upper limit? I'll come to it, don't worry, I'll come to it. So what you did, you were going for order of n, you're trying to see, you saw that whatever the last value you got, this was your answer. Whatever the last value where you were able to fit, like let's keep a previous variable or ans variable, and you'll update your ans variable to 1, to 2, to 3. Okay, then at 4 you are not able to find, so once your canFit function returns 0 or false, you'll return whatever answer you were having till now, so 3. So what I'm saying is, you were doing order of n linear search, which means plus on shorter space, not on this shorter space guys, on this shorter space, 1, 2, 3, 4, 5, 6. Getting it? So what is the way to go? Binary search is the way to go, because binary search is built on top of this thing, order of n plus shorted. You have to go for binary search. Why? Because binary search is built on top of this intuition that linear search, if it is done on shorted array, binary search is the optimal approach. Now see what we do when we get the idea that we have to do binary search. Mostly we do what? We divide the space into 2 regions, favorable and unfavorable, and once we are done with this, we don't even consider these numbers. We are not considering these. They may only confuse you, तुम्हें डराएंगे और कुछ नहीं करेंगे. So what you have to do, see what is your answer. The last favorable is your answer, which means last element of first space, and if you have watched my binary search videos, and especially binary search part 2 video, you know when your L and H is here, so during and at the end of loop, your L will be at first position of second space and H will be at last position of first space. And what you wanted, last element of first space, so H will give you answer. So you got this, that first of all you got the idea that this how to do that binary search on which L and H, the upper limit I will come, but lower limit you can keep, you can start with 1. The lower limit you can start with 1, but upper limit you don't have idea. I'll come back to it later, no problem. But you got that finally, if my binary search is finished, I'll give H as answer, I'll return H directly. Okay, now let's see how to write this canFit function, and I'll write right here, no problem. So let me have this canFit function. It will take number of cows you are having, it will take all this array or position, and it will take, let's say, because you will be calculating mid, obviously you will be calculating mid. So let me take mid. What is this mid? All these elements, because lnh is, if let's say lnh is here, so you'll get mid. So what I say, let's keep a count variable. And what does this mean? Count means how many cows you have fit right now. So initially, obviously, you will fit cow number 1 at 0th index, cow number 1 at 0th index. So what I say, let's keep a previous variable where your current cow is placed. So which is your current cow? First cow is your current cow. So your current cow is placed at where? First position. So okay, first position, which means a of 0. So 1. So now what you have to do, start from first position. If you start from first positions and go till the size of this array, go till size of this array. And what you have to do, how you have to traverse, guys, see, if your next cow, so what I mean, if your current distance ARR of I minus previous cow's distance, where the previous cow's position, if the distance between them is greater than equals to your mid for whatever you are calculating, if this is the case, then what you have to do first, increase the count, that yeah, I can fit this cow, I can fit one more cow, and where? At I. So keep your previous equals to ARR of I. So keep your previous equals to ARR of I, because now your cow, now this cow which you placed right now, it will be placed at where? Previous. And previous is what? ARR of I. So you'll previous will keep the track of your current cow, like where your latest cow is placed, because with the latest cow you'll calculate the next cow's position, that where it can be placed. Okay, obviously, because if you place two cows, then third cow you will not compare its distance with first cow, because because it will be anyway be larger, because this is, if you can fit this, then you can easily fit this. So you have to compare with the adjacent cows, and that is the case here. So when this loop is terminated, like when this for loop is ended, if you can see that if my C and T, if I am able to put at least 3 cows, which means greater than like C cows, you'll return what? You'll return 1. And if your CNT is smaller than C, which means if you are able, in the example, guys, if you see earlier, somewhere we were able to put only 2 cows. Where is that example? I think I removed it here. We were only able to put, like with the 4 distance, we were only able to put 2 cows. And if that is the case, where count is lesser than C, like count is lesser than number of cows you were given, so you will return what? You'll return false. You'll return 0. So this is the idea of canFit function. Now let's see what function is. So here, if you see, so up to this point, I've done just basic input thing, because this is SPOJ problem on SPOJ, so you have to do everything. So I've just shorted this space, the search, that vector that you were given, like the location of those houses or stalls. So your L is 1, and now you see that upper limit, because so this LNH, what were they on number line? If you remember this, what were they were the distances between the cows we were trying to keep, 1 2 3. And so about what is the maximum distance that you can even think of putting between two cows is, which is your final distance, final stall minus initial stall, the first stall, sorry. So this is the maximum that you can even think, because 8 is the maximum distance that between two cows it may be, not more than 8, because there is no stall. If you put your first cow at position 1, and if you think that I'll keep the distance between two cows as 9, so where your second cow would be at 10th position, but 10 is not available right now, correct? So the upper limit will be the last house position minus first house position, which is this one. Okay, so here we are doing that binary search, guys. So if you remember, you can fit function, if you see here, if you are at unfavorable, where will you move? You'll move to like left. You'll move to left. Why? Because you want the first favorable, you want the last favorable. Getting it, guys? You want the last favorable, and when you land at favorable, where would you move? You will move to right. Okay, so that is what your, if your canFit function is giving you 1, so which means you are at favorable, so you'll move to right, and right means L equals to mid plus 1. In the same way, you'll move here. So here, if you see, I did the same thing with this function canFit. So this is actually type 2 problem. If you remember, guys, from my part 2 video, what we are doing here is type 2 problem. So do let me know in comments that you like this problem, and till then, enjoy, and we'll meet in some other problem. Thank you.